Okay, so for the first one, finding the mean, we have to add them all together and divide by how many are there. So that's going to be 19 plus 11 is 30, plus 24 is 54, plus 21 is 75, plus 23 is 98, plus 32 is 130, plus 29 is 159, plus 23 is 182, plus 27 is 199, plus 38 is 237. And there are how many numbers in the list? 10. Remember we said that was n equals 10 is what that was? Did you get 247? Okay, I'll take your word for it. So it comes out to be a 24.7 for the mean. No extra charge for the extra 10. Now for the median, what is the first step for the median? Put them order from smallest to largest. So I'm going to start with the 11, 19, looks like 21, 23, 23, 24, 27, 29, 32, and 38. I'm just going to number them to be sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have all 10 of them. Second step in finding the median is to find the position. And the position is always n times 1/2, or n times 0.5. So n is 10 times 0.5 gives us 5. Now remember we said when n is even, we're going to get that whole number, and it's going to be between that location and the next one, the 5th and 6th number. So the 5th number is 23 and the 6th number is 24. So it's going to be 23 plus 24 divided by 2 is 23.5. That's our median. How do we find the mode?
Number that appears most common.
Number that appears most often, the most common number. And once we put them in order for the median, it's a lot easier to find the mode. We see that the only one that appears twice is 23. Range, how do you find the range? Don't be shy. Largest minus the smallest, so 38 minus 11 is a range of 27. How about the standard deviation? 6 simple steps. There you go. Now, I realize with a 10 number set, that's a little bit cruel, but let's do it anyway. You're probably going to think about what I'm about to do is cheating, and it may be, but I don't care. I'm going to let the computer do the work for me. So I put in my 10 numbers. I am going to subtract my mean, which was 24.7, correct?
Yep.
So I subtracted my mean from each. Then I'm going to square each. So I square them all. Next is to find the total. How many of you got 494.1 for your total? You get that? Okay. Then our next step is divide by n minus 1. Since n is 10, that means we're going to divide by 9, right? So 54.9. Final, that of course would be our variance. Final step. Square root, which gives us our standard deviation. $7.41. Did anybody get that far? Okay.
What's the command for square root in Excel?
In Excel, the command for square root is SQRT. I'm going to leave that open because I might use that later. On a test, I would quiz. I think there's one in my math lab that has like 8 numbers in it that they want you to find the standard deviation for. On a test, I would never use more than 5 or 6 just because I don't want to sit here for 4 hours waiting for people to finish tests. My math lab, they do get a little bit longer. If anybody has like a graphing calculator, let me know and I can show you how to do that stuff on there too. Yeah, those things do amazing things, but yeah, it's almost easier to do it by hand than to remember how to do it with make the calculator do it. By the way, for those of you that are Excel wizards, the command for mean in Excel is equals average. Then you highlight the data set. I missed a number, that's why. There we go, we got our 24.7. For median, it's equals median. We get our 23.5. Mode, it's equals mode. 23, we've already found that. There is no command for range in Excel, but you can use a max and a min to find the largest and smallest, then just subtract them. Standard deviation, STDEV period S. You're specifying to Excel that this is the standard deviation of a sample. 7.409, just like you found. 7.41. STDEV period S. Then open parentheses.
Equals first?
Yep, equals first, yep. You bet. Actually, I think you can get Excel on your phone. They think that you can get Microsoft Office if you have enough memory. You can get the tablet version of Microsoft Office on your phone.
Free?
I do not think it's free. Yeah, I don't know if that one downloads to your phone or not, though. Does it? Have you done it? Okay, I guess WITC. If you use the Outlook in WITC, you can download Microsoft Office as a student user. One of the students here says they were able to load it to their phone, so you might can try that. You bet. Okay, so next I want to look at some measures of position. So I'm going to take this data set we have here and move it down here so we can use it. I'm going to finish off, fill my numbers back in here, the ones I lost. So I've got 1 through 10 here. My data numbers. 10 sets. 10 elements in my set, if I can make myself talk tonight. So n equals 10. So we want to look at measures of position. We talked about mean, median, mode last week. I don't remember, did we get to quartiles at all? Okay.
No, I don't think so.
I didn't think we had either. So actually what I want to start out with tonight is percentiles. Almost all of us have heard it somewhere that you took your test and you tested in the 85th percentile, or your weight is in the 38th percentile, or whatever. You hear the word percentile all over the place. And what the percentile means, let's say you're told that you are in the 38th percentile. That means that whatever item that is that you're measuring, whether it's a test score, height, weight, income, whatever. What that is saying is 38% of all people that have been tested, so we're just going to say 38% of everybody, is less than you, is less than yours. So if you tested in the 38th percentile on a test, you took the admissions test or whatever, so you're in the 38th percentile. That means 38% of the people taking that test have a lower score than you. Of course, the other side of that is 62% have a higher score. So that's where your land is at that point within the data set. So obviously, if you test in the 98th percentile, you've done really well. It's not possible to test in the 100th percentile. The only way you could ever be in the 100th percentile is if you could verify that absolutely everybody in the world is less than yours. So there's only one person in the world that's in the 100th percentile for each category. So how do we find percentiles? Well, first thing I'm going to do is I'm going to find the number that's in a given percentile. So I'm going to move this data set down another notch. To find a number in a given percentile, it is all about position. So the position again is n times the percent. And just like before, if it's a decimal, round up. If it's a whole number, then it's between that one and the next one. I'll show you what I mean here. Do you ever have time to copy down the data set again? Give me a second.
I can just look back on the previous page.
Okay. So let's say I want you to find the 70th percentile in this data set. Well, to do that, I'm going to take n, which is 10, times 0.7. That's 70% as a decimal. What's 10 times 0.7? 7, right? So if I refer up here, that's a whole number. So that's telling me is that's between that position and the next one. So the 70th percentile is between the 7th and the 8th number. So it's between 27 and 29. Just like with the median, I add them together and divide by 2. So the 70th percentile for this data set is 28. Now, if you decide to use Excel for percentiles, Excel does some strange things sometimes. I mentioned last week in statistics, there isn't just one straightforward way of doing everything. There are some different schools. Percentiles, quartiles is one spot where there are some differences of opinion. And Excel uses an extrapolation technique, which is really, really tough to do by hand. So quartiles is one of the things that, percentiles and quartiles is one of the things that Excel does not do very well. I teach statistics for a couple of other colleges as well. And on a test, I can always tell when somebody used Excel to do their tests, because I know exactly what answers Excel will spit out for certain questions that aren't exactly what you would get if you did them by hand. Okay. Find the 28th percentile. Well, to find the 28th percentile, what am I going to do to find its position?
10 times 0.28.
10 times 0.28. Good. And that gives me what? 2.8. Now that one falls under the category of the first one up here, being a decimal, which means we round up to the third position. The third position up here is 21. 21 is the 28th percentile. Find the 43rd percentile. Try that one in your notes quick. See if you can get it. So it's 10 times what? 0.43, which is 4.3. What do we do with that? Round up, yes, to the fifth. Even though it's only 4.3, we always round up. Because if we were to round down to the fourth number, 43% are not smaller than that one. So we have to round up. The fifth number in the list is 23. Now, this is ironic because if we rounded down to the fourth one, it'd still be 23. But we do have to round up. Most of the time, if you round down, it will not work. So that is finding the number that is in that percentile. Now let's go the other way. What percentile is the 29? So in what percentile is the 29, you could have asked. The formula for this is we have the number that are smaller plus the number that are equal divided by 2 all over and the total number that are there. So here, 29 is right there. How many numbers in this list are smaller than 29? Say 7. There we go. 1, 2, 3, 4, 5, 6, 7 are smaller, right? How many numbers in that list are equal to 29? 1. So that's going to be 1 divided by 2. Because the 2 is from the formula. How many total numbers are there in the list? What's n? 10. You got it. So this is 7 plus 1/2 is 7.5. Divided by 10 is 0.75. So I move my decimal point or multiply by 100, however you want to look at it to make it a percent. That is the 75th percentile.
So why is it a half? Why isn't it like 14.5?
Well, because it's considered to be greater than half of the number that are equal to it. Like, let me show.
You're talking about the one number. You're not actually dividing 29 in half.
No, I'm not dividing 29 in half. There's only one number that's equal to 29. Yeah.
Okay.
7 plus 1/2 is 7.5 divided by 10.
So with all these equations, it's basically variation on the same equation. We either flip the ideas or we do something to it so that it, I don't know, kind of work backwards.
Many of them are, yes.
Does that make sense?
Yep. And that's exactly what we're doing here is it's rather than finding what number is in that position, we're finding what position is that number in.
Yeah.
Yep. So looking at, let's say, the 23. How many numbers in this list are smaller than the 23? 3. Very good. How many are equal to 23? 2. Good. So it's 2 divided by 2. Over, and of course, n is still 10. So 3 plus 2 divided by 2, so that's 3 plus 1, is 4. Over 10 is 0.4. Move the decimal point or multiply by 100 or whatever, that is the 40th percentile. What do you think? Not so terrible? Okay. Strongly related to the percentile is something called a quartile. A quartile divides the data into 4 equal sections. In other words, each of those 4 sections has the exact same number of data points in it. Now, it sometimes confuses people. If okay, quartiles is 4, shouldn't there be 4 quartiles? No. If I have, let's say I have a piece of string, and I need to cut it into 4 pieces, how many cuts do I need to make? 3 cuts. So it only takes 3 quartiles to divide the data into 4 equal pieces. There's the first quartile, there's the second quartile, which I'll label Q2, and the third quartile, labeled Q3. To find the quartiles, it's extremely similar to finding the percentiles. Step 1, put the numbers in order again, from smallest to largest. Step 2, the first quartile is found, first quartile position is n times 1/4 or 0.25. In other words, the first quartile is the 25th percentile. For the second quartile, anybody want to guess? Times 0.50. In other words, the 50th percentile. By the way, is there anything else you know of where you take n times 0.5? It's also the median. The median is your 50th percentile. It's also your second quartile. The third quartile should be a little bit predictable by now. N times 0.75, otherwise known as 75th percentile. So if you can find percentiles, you can find the quartiles. The quartiles are a bit more useful, though. The reason for that is they allow us to compare how the data is distributed a little bit more. Whoops. There we go. Had a connection problem there for a second. for example, let's take a look at, I'm going to give you a small data set, and I'm going to put them in order from smallest to largest right off the bat just to make it a little bit simpler for us, make it a little bit quicker. 7, 11, 13, 14, 16, 17, what is that, 6, 20, and 28. So there are 8 numbers. To find quartile 1, or the first quartile, n equals 8 here. So 8 times 0.25 is 2, which is telling me that it is between the second and third. Between 11 and 13 is 12. Quartile 2, which is usually just referred to as the median rather than the second quartile, is 8 times 0.5, which is 4. Tells us it's between the 4th and 5th. So it'll be between 14 and 16. Otherwise known as 15. So the median, or the second quartile, is 15. And finally, quartile 3. 8 times 0.75 is 6. That tells us it's between the 6th and 7th number. So it is between 17 and 19, or 17 and 20, which is 18.5 is the third quartile. The reason this is important is these 3 things combine with the minimum and the maximum to make up something called the 5-number summary. What the 5-number summary is used for is something called the box plot. What a box plot does is I take a number line. So this goes from 7 to 28. So I've got a number from 7 to 28. So I'm going to go 5, 10, 15, 20, 25, 30. My minimum, what's my smallest number here? 7. And my maximum is the 28. So on my box plot at the minimum of 7, I'm going to put a little mark there, a little line there. My first quartile is at 12. So I put a little bit bigger line there. 15, I'm going to put the same size line as at the 12. I'm going to keep it lined up. That's the median. The third quartile is 18.5. That's going to be somewhere in here. I connect the first quartile to the third quartile with the median, just like that. That is the box part of the plot. Now then, my maximum is 28, so that's right up here. So from the upper end of the box, I extend a line out to that 28. From the lower end of the box, I extend the line down to that minimum of 7. Sometimes this is referred to as a box and whisker plot. Those would be called the whiskers. So what you can see here is this, the plot has 4 distinct sections. This is the first fourth of the data. This is the second 1/4 of the data, the third, and the fourth quarter of the data. The bigger that section is, the more spread out the numbers are there. So by looking at this plot, I can see the numbers are most spread out up here in this fourth quarter. If we look up here, yeah, we go from 17 to 20 to 28. They are pretty spread out there. They're the most tightly fit together here in this second quarter. If I look at that section, yeah, it's 13, 14. They're right tight together. Actually, 11, 13, 14, 16, if you want to consider them all together. So that box plot allows us to see kind of how the numbers are distributed with each other. Okay. Now we're going to backpedal a little bit to our mean and standard deviation stuff. What does that all tell us? Well, to understand what that tells us, remember we talked about distribution. And we said that in nature, data tends to be distributed in this bell curve thingy. Well, that one's a little uneven, but oh well. And we said that that normal curve, that bell curve, the mean, median, and mode, if it was a perfectly normally distributed set of data, the mean, median, and mode would all be right at the center. And we said the spread, or the standard deviation, describes how wide that is. And it actually, it's very, very distinct and very, very predictable on how it describes how wide it is. So if this middle number is the mean, it could be called the median or the mode, it doesn't matter, but generally we use the mean to label that one when we're talking about this. If we move down one standard deviation, so minus one standard deviation from the mean, we expect, now there's two different versions of this. What I'm going to talk about is something called the empirical rule. There's an approximate empirical rule which most textbooks use. This textbook chooses to use the exact empirical rule, which is kind of a pain, but it's a little bit more precise. But between the mean and one standard deviation below the mean, the approximate empirical rule just says 34%. Your textbook says 34.13% of the data is expected to be in that range. If we go down another standard deviation, so now we're two standard deviations, so minus two standard deviations below the mean. Between the 1 and the 2 standard deviations, we expect to find 13.59% of the data. And from 2 to 3 standard deviations, we expect to find 2.15% of the data. And below 3 standard deviations. Give me a second, we'll go back and I'll fill in some numbers. I'll make this a little bit more clear. So less than 3, further down than 3 standard deviations below the data, we expect to only find 0.13%. And going the other way, it's the same. 1 standard deviation above. So between the mean and that is 34.13%. From 1 to 2 standard deviations above, we're expecting that 13.59%. From 2 to 3, 2.15 again. And more than 3, we are expecting to have 0.13%. So, what does all this mean? I can almost hear the huh coming from the group. Well, let's say that all students that take this class, the mean grade is 84 out of 100. With a standard deviation of, let's go with a 6. What that is saying is, if I look at this curve, now, these percents that I just filled in here never, ever change. Those percents are constant. What changes is the mean and standard deviation. So the mean of 84 means the middle of this distribution is 84. The standard deviation of 6 means when I go down a standard deviation, I subtract 6. What's 84 minus 6? 78, right? What's 78 minus another 6?
71.
72. 72 minus another 6? 66. Okay. Now let's go the other way. Starting at 84, what's 84 plus 6? 90 plus another 6? 96 and plus another 6? 102, good. Believe it or not, I have had students score more than 100% in this class. I had a student a couple years ago I had to pick on because they were running like 104% in the class going into the final test. So I had to pick on them. Told them no matter what you get on the final test, it's going to drop your percentage. Even a perfect score with 104 goes down, right? So anyway, what does this mean? Well, that means that we expect between 78 and 84, we expect 34.13% of students to be between 78 and 84 for their grade. Bless you. Between 90 and 96, we expect 13.59% of the students to be between those two scores. Between 96 and 102%, we expect only 2.15% of students to be between those two scores. Less than 78. If we add all those up, that comes out to 15.87%. We expect only 15.87% of the students to be below 78. Bless you. And like I said, those percents are the same. What changes are these numbers down here based on what our mean and standard deviation are. So let me show you another example of this. Let's say you decide you want to buy a new home. You want to buy a 3-bedroom, 2-bath home. And you do your research. And when you're doing your research, you find that in this area, the mean cost of a 2-bedroom, 3-bathroom home is $118,000. With a standard deviation of $18,000.
So what do you call the standard deviation?
That's where you'd have to calculate the standard deviation or be given the standard deviation. Remember, the standard deviation is what we calculated where you the 6-step process?
Yes.
Yep. So for something like this, you would have to be given. You'd have to look up what the standard deviation of home sale prices
So
are.
like looking at like 10 homes or whatever and getting that average, and that's when you got your standard
You'd actually have to look at a lot more than that. You'd have to look at, to get an accurate standard deviation, you'd look at all homes sold in the last 4 or 5 years. There's, when you get talking statistics, there are a lot of factors to consider. Like a few years ago, not that long ago, they were only using numbers from like the last 2 years because there was that huge drop in home prices in 2008, 2009. Yeah, the housing crisis. Well, if you went back more than just a couple years, you were getting into those inflated prices before the big price drop. Well, you didn't want to include those in there because home values weren't really worth that much. To be honest, they weren't worth that much back then either. People were just willing to pay that much. So you have to, if there's a major change in the market, you have to adjust the window that you're looking at. But assuming that home prices have been relatively consistent for the last 5 or 6 years, you'd want to go back probably 4 or 5, 6 years and get the average and standard deviation for all those homes sold in that area.
So that would be like in a certain neighborhood also? So we're
Yep.
looking at, okay.
Yeah, you wouldn't want to look at, okay, here is the very, very expensive neighborhood, and then here's the working class neighborhood, here's the, you know, the kind of the, a lot of trailer courts and all that stuff mixed in this neighborhood or whatever, high crime neighborhood, or right next to a school is going to be different. I mean, there's a lot of different factors that come in that affect home values. So you want to decide this is the type of neighborhood I want to live in and then look at just that neighborhood. It's called avoiding extraneous variables. I mean, there's a lot of variables that come in. If a new factory just went in next door, it's going to drop the home values because of the noise and whatever. living next door to a bar compared to living next door to a school is going to affect your home values.
So I went out of the room for a second, and where it said the empirical rule, is that where you're talking about the bell curve?
That's this bell curve and these percents we're talking about.
And
Yep.
so it's always going to be that. It's just whatever
Yep.
you plug into it. Okay.
So I'm going to draw my bell curve again. Trying to draw it a little bit bigger this time. Now these percents never change. This is going to be 34.13% here and here. This is going to be 13.59% here and here. This is going to be 2.15% here and here. And 0.13% here and here. What numbers are going to go down along the bottom? Well, it's easiest to start in the middle. What's going to go in the middle? The 118,000. The mean always goes in the middle. Now I'm just going to write 118. I'm going to leave the zeros off for the rest of this just to make it a little simpler. As I go down, what number would go here? 100,000. How do I get 100,000? Well, it's my mean of 118,000 minus a single standard deviation of 18,000. So that's going to be 100,000 there. I'll put the zeros in to avoid confusion. This next one's going to be 82,000 because I subtracted another 18,000, another standard deviation. What's this last one going to be? 64,000. Going the other way, what number is going to go here? 136,000. There I'm taking my mean of 118,000 and I'm adding the standard deviation of 18,000. What's going to go here? 154,000. I'm adding another standard deviation, another 18,000. And then finally here, 172,000. So now let's say that you are looking at these homes and you find a home that you absolutely love. It's $154,000. And your realtor is putting the pressure on you, saying you need to put in an offer at that price, accept their selling price right now. This house isn't going to stick around very long. Well, looking at this, $154,000 is right here. What that is telling us, if I add up all these percents here that are below it, this is the less than side here that I circled in purple. If I add up all these percents, that's going to add up to 97.72%. What that is telling me is 97.72% of all of the 3-bedroom, 2-bathroom homes that have sold in that area recently have sold for less than $156,000 or $154,000. So, do you think there's a good chance you're going to find a house that's cheaper that you still like? Yeah, 97.72% of them have been cheaper. Hopefully in that 97% you can find one you like.
That's a great tip.
Well, I mean, it applies to everything. If you're looking at taking a job, you want to look at your starting salary or whatever, and you compare it to starting salaries of other people in the area. This tells you where you fall on that curve, or you can get it right down to percents. Now, the problem is, of course, if the number doesn't fall exactly on a standard deviation, it's a little tough. Let's say you find a house that is marked $130,000. Well, $130,000 falls somewhere in here. Well, you know that 50% of the houses, it's higher than half. 50% of the houses are cheaper than that. But you don't really know what how this 34% is split up within that range. I will say that comes out to be at least like 72% are still less than that number. Generally, you want to stay less than one standard deviation above the mean if you're looking at spending money. If you go more than one standard deviation above the mean, puts you at a spot where 84.13% are less than that. That even sounds like you're getting a little steep, but because there's so much in the middle here, you can't get very far away from the middle without having big numbers added on to the 50%. Of course, the middle, if you bought a house that was priced at the mean of $118,000, what percent of the houses would be cheaper than that? Half, right? 50%. Half of the houses would be cheaper than the mean, half of the houses would be more expensive, if this is a normally distributed set of data. Okay, it is time for our break, so let's go ahead and take our break. Come back at 6:30.